All right, today we're going to crack a classic coding interview question. Now, on the surface, it seems pretty simple, but the solution? Oh, the solution is so clever, it's a perfect test of how a programmer really thinks. We're talking about the max stack problem, and trust me, by the end of this, you'll get exactly why it's such a brilliant puzzle.
So just picture this for a second. You're in that high-pressure job interview. The interviewer leans forward and lays out a challenge. You've got this massive collection of numbers, and it's always changing. Numbers are being added, removed all the time. Your job? Find the biggest number in that list at any given moment. And here's the real kicker. You have to do it instantly. So how would you even start to tackle that?
Okay, before we can solve it, we've got to know our main tool here, this stack. And the best way to think about it is like a stack of dinner plates, or maybe even a Pez dispenser. You can only add a new plate to the very top. In programming, we call that a push. And you can only take a plate from the top. We call that a pop. It's what we call a last-in, first-out system. Simple as that.
Now, what makes our problem so tricky is that we're not dealing with just any old stack. A normal stack lets you push and pop. That's it. But the max stack, the one from our interview question, needs a third superpower, a special function called getMax. And this is where the real challenge begins.
You know, the first thing that probably pops into your head is, well, I'll just look through all the numbers every time they ask for the max. And yeah, that would work. It would give you the right answer. But in the world of software engineering, just getting the right answer isn't good enough. You have to get it fast.
And here it is. This is the rule that changes the entire game. The interviewer tells you that push, pop, and especially getMax all have to run in what's called O1 time complexity. This is the one single constraint that separates an okay solution from a truly brilliant one. So what on earth does O1 actually mean?
Let's break this down. O1 basically means constant time. It's, for all practical purposes, instant. It doesn't matter if your stack has 10 numbers or 10 million, the operation takes the exact same tiny amount of time. The opposite of that is On, and that's slow. That means the more data you have, the longer it takes. It's kind of like having to read an entire book from the first page to the last just to find a single word.
And the difference here isn't small, it's staggering. I mean, if an O of 1 operation is a tiny little blip on the radar, an O of n operation is this massive system-slowing spike. Searching through the whole stack every single time, that's O of n. And for our purposes, that is just way too slow. We need that instant O1 performance.
So, how in the world do we do this? How can we possibly know what the biggest number is at all times without actually searching for it? Well, this is where we get to that aha moment, the part that makes this solution so cool.
The big idea, the core insight, is actually beautifully simple. We don't just use one stack, we use two. We'll have our main stack where we put all the numbers, and then we'll have a second special stack that has only one job, to keep track of what the maximum value is at every single step of the way.
Okay, so the logic for adding a number follows a few simple rules.
First, you always push the new number onto your main stack. No surprises there. Then, you just peek at the top of your special max stack. Is your new number bigger than that? If yes, great. Push your new number onto the max stack. It's the new champ. But, and this is the really crucial part, if it's not bigger, you simply push the current max onto the max stack again. You duplicate it.
All right, let's walk through a quick example to see how this works. We push the number 5. Of course, it goes onto the main stack. And since our max stack is empty, 5 is automatically the biggest number so far, so it gets pushed there too. Easy enough.
Okay, next up, we push a 2. It goes right on top of the main stack. Now we check our max stack. The current max is 5. Is our new number, 2, bigger than 5? Nope. So we follow our rule and push the old max, which is 5, onto the max stack again. You see? The stacks are still the same height.
And now, let's push a 7. It goes on the main stack. We look at the top of our max stack, which is currently a 5. Is our new number, 7, bigger than 5? Yes, it is. So this time, our new max, 7, gets pushed right onto the max stack. You can see how it's perfectly tracking the current leader at every step.
And just like that, boom, we've done it. How do we find the maximum value now? We don't have to search anything. We just peek at the very top of our max stack. It's always sitting right there, waiting for us. That's an O of 1, totally instant operation. Problem solved.
But what about removing numbers? Well, the pop logic is just as elegant. To keep everything perfectly synchronized, whenever you pop a number from the main stack, you also pop the corresponding value from the max stack. This little rule makes sure they always stay the same size and perfectly aligned.
Let's see it in action. We pop from our main stack, so the 7 is gone. We do the exact same thing to the max stack, so its 7 is gone too. Now look, what's the maximum number in our list? We just peek at the max stack and it correctly tells us the max is now 5. It just works perfectly.
So, look, this is a fantastic solution to a really neat puzzle. But the reason interviewers love this question is because of the bigger idea it teaches. It's about a really fundamental concept in all of engineering.
When you really boil it all down, this entire solution demonstrates one of the single most important principles in all of software development. It's called the space for time trade-off. Just think about what we did. Our solution uses more memory, right? We're storing a whole extra stack of numbers. But what did we get in return for using that extra space? We got incredible speed. We traded a bit of memory to make our getMax function instantaneous. And that's a choice engineers make every single day. Do I optimize for speed, or do I optimize for memory? And that leaves us with a pretty fascinating question to think about. This trick, using a little extra space to gain a brand new ability, isn't just limited to stacks. So, what other classic data structures out there could be given a new superpower just by being clever and giving them a little extra memory to play with? Something to think about. Thanks for tuning in.